Section 9.2 talks about multi-stage experiments in modeling games. So the first thing we have here is something called the counting principle. And it says if a first experiment can be formed in m distinct ways, and a second experiment can be performed in n distinct ways, then the two experiments in that specific order can be performed in m times n distinct ways. Okay, so let's take a look at the first problem that we have here and see if we can't figure this one out. It says, suppose we toss a fair coin 3 times and record the results in order. Part A says, let's find the sample space for this experiment. Okay, so if we're going to toss a coin 3 times, the first thing I'm actually going to do is I'm going to draw a tree diagram. So if I flip it once, I can get heads or tails, right? And then if I flip it a second time, I can also get heads or tails. And then if we flip it a third time, we can still get heads or tails, right? So for part A, we're going to find our sample space, okay? Now remember, we're going to flip our coin 3 times. So it's possible that we get a heads, and a heads. So this would be one possibility. Or we could get heads, and tails. Heads, tails. Or we can get heads, tails, and heads. Heads, tails, and heads. Or we can get heads, tails, and tails. Okay. Or we could get tails, heads, and heads. And I'm just going through all the possibilities here, right? Tails, heads, and heads. Or tails, heads, and tails. Or tails, and heads, or tails, and tails, right? Okay, so there's part A. Now, part B says, let's find the event A that has 2 heads and 1 tails. Okay, 2 heads and 1 tails. So I'm going to look here, see if I can find 2 heads and 1 tails. There's one of them, so we could get heads, and tails. 2 heads and 1 tails. Here's another one. Heads, tails, and heads. 2 heads and 1 tails. And looks like this might be the last one. Tails, heads, and heads, right? Okay. Now, part C says, let's find the event B of tossing no tails. So if we're not going to have any tails, then it would just be that one heads, right? And then part D is in dog. The event C is going to be tossing a heads, tossing a heads on the last toss. Well, that one has it on the last toss, doesn't it? Because it's right there. This one has it on the last toss. Okay. This one has it on the last toss. Let's see. And this one has it on the last toss. Okay. And so there are our events. Okay. So one thing I really want to point out here, y'all, is when I draw my tree diagram, really helps me out because I'm able to visualize what's going on, okay? So tree diagrams, I think, are really, really helpful. Let me go ahead and move on to the next one here. And it says 3 coins are tossed. So I want you to notice here is the same tree diagram that we drew over here. It's just a whole lot smaller. Use the tree diagram to count how many ways the outcome consists of 2 heads and 1 tails. Okay, 2 heads and 1 tails. So 2 heads and 1 tails. You know what? I'm actually going to use my sample space from up here. If I want 2 heads and 1 tail, hey, you know what? Didn't we do that in part A already? 2 heads and 1 tail? Yeah, we did. So this answer would actually be the same thing here. Heads, tails, tails, heads, heads, and tails, heads, and heads again, right? Okay, so we'd actually already done that one there. Okay. All right, now let's take a look at the next one here. Oh, come on, my pen is freezing up. I don't know why it does that, but it doesn't. There we go. Okay, so it says 2 marbles are drawn without replacement from a box containing 3 white, 2 green, 2 red, 1 blue. Okay, so the first thing I'm going to do, I'm going to figure out how many marbles we have total. So 3 and 2 is 5, 2 more is 7, 1 more is 8. Okay. So we're going to draw, so we have our marbles in a box here, right? And we have 1, 2, 3 red. We have, no, 3 white actually. So I'll tell you what, let's go like this. 1, 2, 3, I'll just use black for now. 2 green, 1, 2, 2 red, 1, 2, and 1 blue. Can I change my color here? Yes, we can. 1, okay, there we go. 1 blue, okay? And I want you to pretend for me that, here we go, those are white, okay? We want to find the probability that both marbles are white, okay? So, the probability that we're going to get a white on the first try, remember, we have 8 marbles, right? Okay, so how many of them are white? 3 of them are white, right? That doesn't look like a good 3. Let's do that again. There we go. Okay, what's the probability that we're going to get a white the second time? Now notice what it says. It says without replacement. So once we choose a marble, it's not there anymore. So that's what without replacement means. We didn't put the marble back. So now, how many marbles do I have? Now I only have 7. And if we chose a white the first time, how many marbles would be white this time? Only 2 of them. So I'm going to take 3 out of 8. I'm going to multiply it by 2 over 7. And before I do that, we can reduce this one here and this one here. 1 and 4. And now we can multiply straight across. That's 3 over 28. Okay. All right. So let's do another one similar to that, okay? So I'm going to draw my box again right here. Okay. 3 white, so 1, 2, 3. 2 green, 1, 2. 2 red, 1, 2. And 1 blue. 1, right? So we still have 8 marbles, right? Okay, so it says we're going to find the probability that the first one is white and the second one is blue. So now let's go, what's the probability that we're going to get a white marble? Again, out of 8, 3 of them are white. Now, again, we are not replacing the marble. So now we want to figure out what's the probability we're going to get a blue marble. Once we choose one, so we chose a white one, right? That was our objective. So now there's only 7 marbles left, right? What's the probability that the second one is going to be blue? Well, there's only 1 blue marble, right? So I'm going to take 3 out of 8 times 1 out of 7, and that'll leave me with 3 over 56, right? Okay. So let's take a look at the next problem. It's similar to the one we did, except instead of using marbles, they're using letters, okay? Excuse me, and it says a box contains the 6 letters sample, right? Those letters right there. 4 letters are drawn one by one, but notice what it says here now. Oh, come on, my pen froze again, guys. Sorry about that. There we go. Now it says with replacement and are recorded in order. What's the probability that the outcome is these letters here? Okay. So these are the letters that we can choose from, okay? And we're going to choose 4 letters, okay? So what's the probability that the first letter we choose is the letter P? Well, how many letters do we have? We have 6 letters. And how many P's are there? Well, there's just one. But I want you to notice something. It's with replacement. So even if I chose the letter P the first time, the second time, because we are replacing the letter, all that means is I'm putting the letter P back. So now, what's the probability that I'm going to choose the letter A? Well, there's only one A out of those 6, right? But again, once I choose the letter A, we're going to put it back because it says with replacement. So we're putting that letter, even though we chose it, we're putting it back in there. That's what with replacement means, okay? What's the probability that we're going to choose the letter L? Well, there's only one L out of the 6. And what's the probability that we're going to choose the letter E? There's one E out of the 6. And I'm just going to multiply them straight across. Those are 6s, by the way, guys, not zeros. Okay. So I know that's going to give me 1. Okay. And let me grab my calculator real quick, like right here. Notice how many 6s we have. We have 4 of them, right? So if I wanted to figure out what's 6, I mean, I could do it 6 times 6 times 6, or I could just go, what's 6 to the 4th? And I'm coming up with 1296. And so there's my answer, okay? All right. Let's see. It says a box contains the following mixture of colored marbles. We have 3 black, 1 red, 4 yellow, and 3 green. If 2 marbles are drawn and the second being drawn after the first is replaced, what is the probability that they are both black? Okay, so let's do the same thing we've done before. Okay, so 3 black. 1, 2, 3. 1 red. 1 red. Let's go to the green because there's 3 green. 1, 2, 3. And they said there's 4 yellow. 1, 2, 3, 4. Okay, there are my 4 yellows. Okay, now it says if 2 marbles are drawn and the second is being drawn after the first one is replaced. So we're still just replacing this, right? What's the probability that they are both black? Okay. So how many marbles we have? We have 3, and that is another 4 is 7, and another 4. It looks like we've got a total of 11 marbles, right? So 3 out of 11, okay? And then we're going to get another black marble, but we replaced it. So there's still 3 out of 11. So 3 out of 11 times another 3 out of 11 should give me 9 out of 121. Okay. All right. So now let's take a look at the next one here, and it says a box contains a following mixture of colored marbles. Okay, so we're still dealing with marbles here. How many do we have? We have 3 black. 1, 2, 3. We have 4 red. 1, 2, 3, 4. We have 1 green, and you know what? Let me see if I can change this one here. Is there a yellow? Yeah, that's yellow enough. And how many yellows do we have? 4. 1, 2, 3, 4. There we go. Just a little easier to see than the highlighter. Okay. So it says, what is the probability of drawing in order a yellow marble, a red marble, and a black marble if the 3 marbles are drawn without replacement? Okay, so the first thing is, what's the probability that we're going to get a yellow? Okay, so how many yellows did we have? We had 4 yellows. What was the total number of marbles we had? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Looks like we have 12. Okay. All right. And now we're not going to replace it, right? So we chose, say, a yellow marble. Now we're going to say, what's the probability of getting a red marble? Okay. Now notice, we only have 11 marbles to choose from now. How many of them are going to be red? Well, 4 out of the 11, right? And so suppose we chose a red marble. We got that one out of the way, okay? And now we want to find what's the probability that we're going to get a black marble now. Now remember, we used to have 12 marbles. We chose 1. Then we had 11. We chose one. So now we're only left with 10 marbles. How many out of these 10 are black? 3. Okay. So now I'm going to take 4 out of 12 times 4 out of 11 times 3 out of 10. Okay, let's start reducing our fraction. We can divide both of those by 4. So let's see, that's going to give me 1/3. I can reduce this one and this one by 2. So that'll leave me with a 2 there. That'll leave me with a 5 there. I'll leave this 11 here, and I'll leave that 3 there. But again, if you notice, we can get rid of these 3's. So that becomes a 1, and that becomes a 1. So let's multiply straight across. 1 times 2 is 2 times 1, still 2. 1 times 11 is 11. 11 times 5, 55, right? Alrighty. So we have something called independent events. It says event A and event B are independent if the occurrence of either event in no way affects the probability of the occurrence of the other. Okay. So let's take a look here. It says, what's the probability of spinning an A on this spinner? So let's figure out, let's see, we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 choices, right? How many of them have the letter A? 1, 2, 3 out of 8. Right? 3 out of 8. Okay. Let's take a look at the next one here. It says, what is the probability of a dart landing in region 1? Okay, so guys, look at the way my picture is drawn. Basically I have a square, and this is region 1, region 2, region 3. Why don't we do this? That's not a very straight line, Omar. We can do better than that. Let's go. Okay. Still got a little bit messy, but I think you know what I'm trying to do. Okay, there we go. So now our square is cut up into 4 equal portions. These are both region 2. Okay, the fact that we drew a line through it doesn't mean it's not region 2, it's still region 2. We want to know what's the probability of landing in region 1. Well, out of those 4 equal triangles, right? Triangle, 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 triangle. One of them has the region 1. Okay. Let's take a look here. It says, what is the probability of a dart landing in the shaded region? Okay. So again, what I want to do is I want to make sure that this piece is cut up into equal portions, okay? So guys, if we were to kind of do this here and this here, then we could say 1, 2, 3, 4, 5, 6, 7, 8. This is cut up into 8 pieces. And out of those 8 pieces, how many of them are shaded? We would say 3 of them, right? 3 out of the 8. Okay. Alrighty. So the next problem that I got here says, assume that the probability is 1/2 that a child born is a boy. What is the probability that a family with 3 children has just 1 boy? Okay, so let's do this. We're going to find what happens if we have 3 children. Okay, so if we have a child, that child can either be a boy or it can be a girl. That will be our first child. And then our second child can still be a boy or a girl. And our third child can still be a boy or a girl. Okay. So I'm going to write out my sample space. Okay. So we can have a boy, a boy, a boy, a boy, a boy, and a girl. Or we could have a boy, a girl, and a boy. Or we could have a boy, a girl, and a girl. Or we could have a girl, a boy, and a boy. We could have a girl, a boy, and a girl. We could have a girl, and a boy. Or we could have 3 girls, right? Okay. So, how many are in my sample space? 1, 2, 3, 4, 5, 6, 7, 8. So I know my probability is going to be out of 8. And it says, what's the probability that a family with 3 children has only one boy? So here's one boy. Here is one boy. And here is one boy. So 3 out of the 8 would that would be the probability of having a family that just has one boy, right? Alrighty. Okay, let's take a look here. So this next problem, I'm going to kind of show you how to do this problem using something called a Venn diagram. You might have seen this in Math for Teachers Part 1, but if you didn't, I'm going to walk you through it here, okay? So it says, at a certain hospital, 40 patients have lung cancer, 30 patients smoke, and 25 have both lung cancer and they smoke. So it says, suppose a hospital has 200 patients, and if a patient is chosen at random, is known to smoke, what's the probability that they also have lung cancer? Okay, so let's see if we can do this using a Venn diagram. Okay, so I'm going to go like this, and like this, and like this. Okay, so how about if we say these are going to be the ones that have lung cancer, and these are going to be the ones that smoke. So we know that there's a total of 25 who have lung cancer and they also smoke, right? Okay. Well, if 30 patients smoke and 25 of them have lung cancer and they smoke, that would tell me that these 5 here smoke, but they don't have lung cancer, right? Because everybody in this circle of the smokers has to add up to 30. Now, same thing over here. We have 40 patients that have lung cancer. 25 of those patients with lung cancer also smoke. So if I were to subtract those numbers, that would give me 15. And I know that would be accurate because everybody in this circle has cancer, and there's a total of 40 of them, right? Okay. So now it says if a patient chosen at random is known to smoke, okay, what's the probability that they also have lung cancer? Okay, so we want to know, out of those people who smoke, how many smoke? 30. Out of those that smoke, what's the probability that they also have lung cancer? 25 out of those 30. And if I divide them out, if I divide them both by 5, that would give me 5, 6. And I think that was, yep, that's all of 9.2.